In October 2025, a machine sitting in a lab in Santa Barbara, California did something that, for most of computing history, wasn't supposed to be possible for decades yet. It solved a real physics problem, not a rigged puzzle, not an abstract benchmark designed to look impressive, in just over 2 hours. The exact same calculation, run on the fastest supercomputer human beings have ever built, was estimated to take 3.2 years. Not 3.2 hours, 3.2 years. That's a speed up of roughly 13,000 times. And the team that pulled it off calls itself, quite literally, Google Quantum AI. This isn't hype dressed up as science. It's a peer-reviewed result, published in the journal Nature, confirmed independently, and this part matters more than the headline number, designed specifically so other scientists could check it and get the same answer. That last detail is the actual story here, and by the end of this video, you'll understand why it matters more than the 13,000 times number that's been all over headlines since. Here's why that distinction is worth 40 minutes of your attention. Quantum computing has made huge, splashy claims before, and more than once, those claims fell apart within weeks once rival researchers got a look at the fine print. So this video isn't just going to hand you the impressive number and move on. We're going to walk through what the machine actually did, why the team building it went out of its way to make the result checkable by outsiders, where independent experts still have legitimate questions, and what a result like this actually opens up over the next 5 to 10 years, as opposed to what it doesn't. Let's start from the beginning, because to understand what just happened, you need to understand what quantum computers have and haven't been able to do, and why the field has spent years being publicly, repeatedly, embarrassingly wrong about its own milestones. A regular computer, the one you're watching this on, stores information as bits, ones and zeros, on or off, nothing in between. Every photo, every video, every calculation your phone has ever run comes down to enormous strings of those two states, flipped billions of times a second. A quantum computer doesn't work that way. It stores information in qubits, and a qubit can exist in a mixture of both states at once, a property called superposition. When you link multiple qubits together, they can also become entangled, meaning the state of one is tied to the state of another, no matter how far apart they are. In theory, this lets a quantum computer explore a staggering number of possibilities simultaneously, instead of one at a time, for certain kinds of problems. That's the difference between a calculation taking seconds and one taking longer than the universe has existed. In practice, qubits are almost unbelievably fragile. They lose their quantum state, a process called decoherence, from stray heat, electromagnetic interference, even cosmic rays passing through the chip. For most of the last 2 decades, the central engineering problem in quantum computing hasn't been building more qubits. It's been keeping the ones you have from falling apart before you can finish a calculation. Add more qubits without solving that problem, and you just get more noise, faster. This is why the field has a credibility problem it's had to fight through in public. In 2019, Google announced that its Sycamore processor had achieved what it called quantum supremacy, completing a calculation in about 200 seconds that the company claimed would take the world's best supercomputer roughly 10,000 years. It was a real headline moment. It was also almost immediately disputed. IBM published a rebuttal arguing that with better classical techniques, the same calculation could be done on a supercomputer in a matter of days, not millennia, shrinking Google's advantage from 10,000 years down to something closer to an inconvenience. And critics pointed out something more fundamental. The task itself, called random circuit sampling, had no real-world use. It was chosen specifically because it was hard for classical computers, not because anyone needed the answer for anything. You couldn't verify the result was even correct without a classical computer capable of checking it, which somewhat defeated the point of claiming an advantage in the first place. This is why the field has a credibility problem it's had to fight through in public. In 2019, Google announced that its Sycamore processor had achieved what it called quantum supremacy, completing a calculation in about 200 seconds that the company claimed would take the world's best supercomputer roughly 10,000 years. It was a real headline moment. It was also almost immediately disputed. IBM published a rebuttal arguing that with better classical techniques, the same calculation could be done on a supercomputer in a matter of days, not millennia, shrinking Google's advantage from 10,000 years down to something closer to an inconvenience. And critics pointed out something more fundamental. The task itself, called random circuit sampling, had no real-world use. It was chosen specifically because it was hard for classical computers, not because anyone needed the answer for anything. You couldn't verify the result was even correct without a classical computer capable of checking it, which somewhat defeated the point of claiming an advantage in the first place. That episode set the tone for years of back and forth in the field. Every time a lab announced a new milestone, we're working more qubits, longer coherence times, a faster benchmark, rival researchers would comb through the claim looking for the same kind of gap IBM had found in 2019. More often than not, they'd find one. Quantum computing, as a field, spent the early 2020s in an odd position. Hardware kept improving on paper, qubit counts kept climbing, but the actual gap between impressive lab demonstration and something a working scientist could rely on barely moved. The problem was never really about raw qubit count. It was about noise. Add 10 more qubits to a chip without also improving how well you protect them from decoherence, and you don't get a machine that's 10 qubits more powerful. You get a machine that fails 10 qubits worth of times faster. That history matters, because it's exactly the shadow Google has spent the years since trying to get out from under. And it's exactly why the language you'll hear around October 2025's result is deliberately different. Google isn't calling this quantum supremacy. They're calling it verifiable quantum advantage. And the word verifiable is doing an enormous amount of work in that phrase. Before quantum echoes, there was Willow. Willow is Google's superconducting quantum processor, unveiled in December 2024, built specifically to attack the decoherence problem head-on rather than just adding more qubits and hoping for the best. Its headline achievement at the time was demonstrating that quantum error correction could actually improve as you scaled up. That adding more physical qubits to protect a single logical qubit made the system more reliable, not less, crossing what researchers call the error correction threshold. That might sound like a small technical detail. It isn't. For years, error correction in quantum computing had worked against engineers rather than for them. Every added qubit was one more fragile component that could fail, making bigger systems less trustworthy, not more. Willow was the first system to convincingly show that trend reversing. That foundation, a chip that gets more reliable as it scales rather than less, is what made the October 2025 result possible at all. To understand why, you have to understand what the team actually asked Willow to calculate. The algorithm behind this breakthrough has a name that sounds almost deliberately unglamorous, an out-of-time order correlator, or OTOC. Google gave it a better public name, quantum echoes, and the metaphor behind that name is the fastest way to understand what it's actually doing. Picture sending a sonar pulse out into murky water. It travels forward, bounces off something, and comes back as an echo. And the shape of that echo tells you something about what it hit. Quantum echoes does something conceptually similar, but inside a quantum system instead of water. The algorithm sends a signal forward through a chaotic, tangled quantum system, nudges one single qubit, and then runs the whole process in reverse, effectively rewinding time on the system to listen for how that tiny nudge echoes back. The way that echo comes back, amplified through quantum interference, reveals extraordinarily fine details about how information scrambles and spreads through a complex quantum system. Why would anyone care about that? Because scrambling, how disturbances propagate and get lost inside a chaotic system, isn't just an abstract curiosity. It's a real physically meaningful quantity that shows up in the study of magnets, in the behavior of molecules, and, more surprisingly, in theoretical physics, work on black holes, where OTOCs have been used for years as a tool to study how information behaves at a black hole's event horizon. This is precisely the distinction the Google team wanted to draw against the 2019 controversy. OTOCs are not an artificial puzzle invented to be hard. They are an existing, physically meaningful quantity that physicists already care about and already try to measure, using tools like nuclear magnetic resonance, the same underlying physics behind an MRI machine. That's the key difference between this result and the 2019 controversy. Random circuit sampling measured nothing except how good you are at random circuit sampling. An OTOC measures something that shows up in real physics, in real chemistry, in real materials, which is exactly why Google structured the entire demonstration around proving both speed and correctness at the same time. Here's how the actual experiment worked. Using 65 of Willow's 105 qubits, the team ran the quantum echoes algorithm to measure a specific, higher-order version of the OTOC calculation, one deliberately chosen because it satisfies two conditions that matter enormously to physicists. It can be measured with a strong enough signal to trust the result, and it sits in a computational regime where no known classical method, exact or approximate, can reproduce it in any reasonable amount of time. Collecting the full dataset for the largest version of this experiment took Willow about 2.1 hours, including calibration and the actual readout of results. The team then estimated, using genuine, rigorous classical simulation techniques, not guesswork, what it would take to reproduce the same calculation on Frontier, the multi-exascale supercomputer at Oak Ridge National Laboratory that currently ranks among the fastest classical machines on Earth, built for more than 9,000 GPUs. Their estimate, about 3.2 years of continuous operation, 2 hours versus 3 years. That's the 13,000 times figure you've likely seen in headlines. And unlike some past quantum claims, this one comes with the actual math behind it published alongside the result, openly inviting other researchers to check the classical cost estimate themselves. Hartmut Neven, who leads engineering for Google's quantum efforts, summarized the achievement by pointing to two things together: a genuine computational advantage and a chip fast enough to make that advantage real rather than theoretical. This is the part of the story that gets lost in the 13,000x headlines, and it's arguably the more important half of the announcement. In the 2019 Sycamore experiment, the output was a string of random bits, the kind of result that's almost impossible to independently confirm without an equally powerful classical machine to double-check it, which is part of what made the eventual IBM rebuttal possible. Quantum Echoes was built differently from the ground up. Instead of producing an unverifiable string of randomness, it produces a specific, physically meaningful number, an expectation value, that can be independently reproduced by running the same algorithm on a second quantum computer of comparable quality or cross-checked against physical measurements from real laboratory experiments. That distinction is what separates a magic trick from a scientific result. According to Thomas O'Brien, a staff research scientist on the Google Quantum AI team, the entire point of verification is that it's what opens the door to actual applications. A result nobody else can check is a result nobody else can build on. And Google didn't stop at the theoretical claim. In a joint proof-of-principle experiment with the University of California, Berkeley's Pines Magnetic Resonance Center, the team applied the same underlying physics, using nuclear magnetic resonance, or NMR, the technology behind both chemical structure analysis and medical MRI scans, to study two real molecules, one built from 15 atoms and another from 28. Their quantum-derived results matched what was expected from established methods, effectively acting as a working demonstration that the same echo technique could function as an extended molecular ruler, one capable of measuring atomic scale distances and interactions with more reach than conventional NMR alone currently allows. That's not a hypothetical use case dreamed up for a press release. It's an actual working demonstration on actual molecules, using techniques already central to how chemists and biologists study drug candidates, batteries, and new materials today. Now, here's where I have to slow this down, because this is exactly the point where a lot of coverage and a lot of the more excitable corners of the internet start overselling what actually happened. This is not a general-purpose quantum computer that outperforms your laptop at everything. It's not AI in the sense of a chatbot or a reasoning system. Quantum AI is simply the name of the Google research division, the same way a hospital's cardiology department isn't a robot. And this result did not solve every hard problem in physics, chemistry, or computing overnight. What actually happened is narrower and more honest than that. Researchers built a specific algorithm, tailored to a specific physically meaningful quantity, that runs dramatically faster on this particular quantum hardware than any known classical method can currently match. And they built in a way to check that the answer is actually correct. Independent commentators covering the announcement have been careful to note this distinction. As one detailed technical write-up following the announcement put it, the Quantum Echoes algorithm is deliberately engineered to push into a regime that's hard for classical computers, using highly chaotic circuits and a clever time reversal trick, meaning this solves a very specialized task, not physics in general, and you won't be using an OTOC calculation to do your taxes. There's also the matter of independent replication, which hasn't fully happened yet in the way the 2019 result eventually did. IBM has continued advancing its own hardware roadmap and has not, as of this recording, published a comparable OTOC demonstration of its own. Google's own paper notes that the calculation involves a deliberately chosen, physically meaningful observable, specifically a higher order version called OTOC 2, chosen because it satisfies criteria for both measurability and classical hardness at the same time. And while the classical cost estimate is based on rigorous simulation techniques rather than marketing math, estimated is still doing real work in that sentence. Nobody has actually run the comparison calculation on Frontier for 3.2 years to confirm the number. It's a careful extrapolation from known classical algorithms, using what researchers call tensor network contraction methods to estimate the cost of the best available classical approach. That's standard defensible practice in the field. Google's team reportedly subjected their own hardness claims to a red team analysis, deliberately trying to find a faster classical method before publishing. But it remains an extrapolation, not a completed side-by-side race. It's also worth being precise about scale. The headline experiment used 65 of Willow's 105 available qubits, not the full chip, and nowhere near what would be required for a general-purpose, fault-tolerant quantum computer capable of tackling arbitrary problems. Google itself, in its own announcement, was careful to frame this as a step toward real-world application rather than the arrival of one. The molecular NMR proof of concept used two small molecules, 15 and 28 atoms respectively. Size is chosen because they're well-characterized enough that existing methods could confirm the quantum-derived answer was correct, not because they represent the complex 100-plus atom drug candidates the pharmaceutical industry actually needs modeled. Researchers involved in that side of the work have been explicit that this early-stage result has not yet demonstrated a quantum advantage over classical chemistry methods on real, industry-relevant molecules, only that the underlying approach checks out on cases small enough to verify by hand. None of that makes this any less real. It just means the honest version of this story is a specific and hard, physically meaningful problem was solved by quantum hardware dramatically faster than the best-known classical method, in a way built to be checked by others. Not quantum computers have surpassed classical computers. Full stop. Those are very different claims, and only one of them is what actually happened. So if this isn't a universal quantum supercomputer, why does it matter this much? Because for the first time, the field has a working example of the exact loop that turns a lab demonstration into an actual scientific tool. A physically meaningful measurement, produced faster than any classical alternative, that other scientists can trust because they can check it themselves. That loop, meaningful, fast, verifiable, is the thing quantum computing has been trying to close for over a decade. And it's the reason researchers across the field, not just at Google, have treated this differently than past headline claims. The near-term applications researchers are pointing to aren't science fiction. Modeling how molecules fold and bind is foundational to drug discovery. Figuring out whether a candidate compound will actually latch onto the protein it's designed to target. Modeling the atomic structure of new materials underpins the search for better batteries, more efficient solar cells, and superconductors that work at higher temperatures. All of these problems come down, at some level, to simulating how atoms and particles interact, precisely the kind of chaotic, information-scrambling quantum behavior that Quantum Echoes was built to measure. Google's own framing, echoed by outside researchers on quantum chemistry and material science, is that techniques like this could eventually function as a kind of extended molecular microscope, a way of seeing chemical structure and dynamics with a level of resolution that today's classical tools, including conventional NMR, simply can't reach on their own. That's a 5 to 10 year horizon of practical work, according to people in the field, not a next year product announcement. But it's a horizon with an actual first working demonstration behind it now, rather than only a roadmap slide. It's worth knowing that Google isn't operating in a vacuum here, and that context matters for how much weight to put on any single announcement. IBM continues to push its own quantum roadmap, with processors like its Heron and Nighthawk systems, and has committed substantial computing access to U.S. Department of Energy research efforts aimed at discovering new quantum algorithms using AI-assisted methods. Microsoft has been pursuing an entirely different physical approach with its Majorana chips, based on a more exotic, theoretically more error-resistant kind of qubit, with a stated goal of a scalable, fault-tolerant quantum computer by the end of the decade. Other players, from D-Wave to a growing list of specialized quantum hardware startups, are pursuing their own architectures and their own claims to early advantage. This is a genuinely competitive, genuinely fast-moving field right now with real money. U.S. government funding, corporate R&D budgets, national research initiatives, being poured into it on a scale that wasn't true even 5 years ago. That competition is actually a reason for more confidence in this result, not less. A claim like Google's doesn't sit unexamined. It sits in front of a community of rival labs and researchers who have every incentive to find a hole in it. The same way IBM found a hole in the 2019 supremacy claim within weeks. The fact that the Quantum Echoes result has stood up through months of scrutiny since October 2025 without a comparable rebuttal to the one that deflated Sycamore is itself part of why the field is treating this one differently. It's worth pausing on the name itself, because quantum AI isn't just a branding flourish. The connection between artificial intelligence and quantum hardware has become a real working part of how this research gets done on both sides of the equation. On one side, AI is increasingly being used to design the quantum systems themselves. Microsoft has reported that its Majorana 2 chip, a very different topological approach to qubits, built to be intrinsically more resistant to the noise that plagues superconducting designs like Willow, was developed with help from an internal agentic AI research platform accelerating the underlying materials science. IBM has committed $50 million in quantum computing access to support the U.S. Department of Energy's Genesis mission, with a specific research effort using agentic AI to discover new quantum algorithms by working backward, starting from existing algorithmic techniques and searching for which real-world scientific problems they might solve, rather than starting from the problem and hoping an algorithm exists. Separately, researchers combining a large qubit processor with a new error correction technique have demonstrated something called quantum-enhanced neural architecture search, using quantum hardware to optimize the design of AI models themselves, cutting a process that normally takes weeks down to hours. On the other side, quantum hardware is increasingly being framed as a future accelerator for AI workloads that classical chips struggle with, problems involving enormous combinatorial complexity, the kind that show up in optimizing large models or simulating physical systems for training data. None of this means quantum computers are anywhere close to running the kind of AI chatbots and assistants people use every day. That's not what any of these systems are built for, and nobody in the field is claiming otherwise. But the two fields are no longer developing in isolation from each other. Google's own division carries the quantum AI name specifically because its research increasingly sits at that intersection, using machine learning techniques to help calibrate and control Willow's qubits, while also exploring how quantum processors like Willow might eventually help train or optimize AI systems in return. That convergence is part of why 2025 and 2026 have felt like an inflection point to people who track this field closely, rather than just another year of incremental qubit count announcements. It's not one breakthrough. It's a hardware milestone, a verification milestone, and an early but real fusion of two research fields that used to run on almost completely separate tracks. So where does this go from here? Not toward some singular dramatic moment where quantum computers suddenly take over. That's the fictional version of this story, and it's not how the field actually works. The realistic version is slower and, honestly, more interesting. Incremental scaling of qubit counts alongside continued error correction improvements, more physically meaningful algorithms built the way quantum echoes was built, chosen because they matter, not because they're merely hard, and a slow, steady expansion of real proof-of-principle experiments like the NMR molecule study into genuinely useful chemistry and material science tools. The two things worth watching for next are straightforward. First, independent replication, whether other labs, using their own quantum hardware, can reproduce a quantum echo-style OTOC measurement and get a matching answer, which would be the real end to any lingering 2019-style skepticism. Second, whether the molecular ruler NMR technique scales up from quorum-sized quorum molecules, 15 and 28 atoms, to the far larger and more complex molecules that actually matter in drug development and materials research. That's the test that decides whether this becomes a genuine laboratory tool or stays a compelling but narrow physics demonstration. Either way, what happened in October 2025 is real, published, and the most substantive step the field has taken since the original supremacy controversy 6 years earlier. Not because of the 13,000 times number itself, but because, for the first time, that number came with a way for the rest of the scientific world to check it. That's what a discovery looks like when it's built to last past the headline. What do you think the more important milestone here actually is? The speed or the verifiability? Let me know in the comments, and subscribe if you want the follow-up the moment independent replication actually happens.